Yeah, very good morning to one and all. We welcome you to the last day of this ATAL Faculty Development Program on Sparse Signal Processing and its applications. Today is day 5 and we are going to have sessions 13 and 14. Both are being taken by our expert speaker Dr. SANTOSH NANNURU from IIIT Hyderabad. The topic of today's session is direction of error estimation using compressive sensing framework. In this brief background, I request Ms. Ashoda to give the complete introduction of a brief introduction of Dr. Santosh Namar.
Thank you, sir. Good morning, all. It gives me immense pleasure to introduce the eminent speaker of the session, Dr. Santosh Nannuru. I welcome you, sir, on behalf of the Department of Electronics and Communication Engineering, NIT Andhra Pradesh. Dr. Santosh Nannuru has completed his BTech and MTech dual degree from IIT Bombay in 2004 and 2009 respectively, his PhD from McGill University, Canada in 2015. Now the work experience. Dr. Nannuru has worked as design engineer from 2009 to 2010 at ICOA Semiconductors and Audio Engineering Group, developing noise suppression algorithms. Internship in research in mass transport approach to Monte Carlo filtering in 2012 at Oxford University. He was the postdoctoral research from 2016 to 18 at Scripps Institution of Oceanography UCSD. During his postdoctorate, his research areas were compressive sensing, sparse sensor arrays, DOA estimation, where he developed compressive sensing algorithms for processing underwater acoustic signals. He also worked on sparse sensor arrays for identifying more sources than sensors. Presently, he is working as assistant professor at IIIT Hyderabad. He is working there since 2018, affiliated with Signal Processing and Communications Research Center, SPCRC. Awards. He, uh, he got the Inspire Faculty Award uh, from 2018, presently, 2018 to 2023, McGill Engineering Doctoral Award MEDA from 2010 to 2013, and IIT Bombay High Tech Fund Scholarship from 2007 to 2008. Publications. Dr. Santosh Nannuru has published more than 7 journals with reputed publications like Elsevier Signal Processing, Journal of the Acoustical Society of America, IEEE Signal Processing Letters. Dr. Nannuru has attended and presented his work in more than 7 international conferences. Research interest. His research interests include signal processing, compressive sensing, Bayesian analysis, acoustic signals, area signal processing, sparse arrays, DOA estimation, localization and tracking, particle filters, random finite sets. Now I request our expert speaker, sir, to proceed with the session. Thank you.
Okay, thank you, Dr. Kishore and Yashoda, for the kind introduction. Um, so I'll share my screen now. So just before we start the format, so I'm not sure if there is a set format, but I will be using slides which are embedded in some notes writing software, so I can write also. And in between, if anyone has question, they can ask, they can unmute themselves and ask me, so there's no problem. Or else if there are questions on the chat, which if I'm not able to see those, the organizer or someone can just interrupt me and ask me to look at them. So that's also fine. So is this format fine with everyone?
Yes, sir.
Okay, okay. So I will probably turn off my video and share the screen. Okay. Uh, 1 minute. Okay, you can see my slide. See my screen.
Yes, sir. Yes, it is visible.
Okay, just 1 minute. Yeah. Okay, so let us begin. So today I'll be covering the topic of direction of arrival estimation. So it's a it's a research problem which has been investigated for a long time. Many decades people have been working on it, and there have been solutions, various solutions. Tried for this problem at various times, and many of them are popular still today. Uh, so what we'll be looking at today more specifically is how to solve this problem, find directions of arrivals within the framework of compressive sensing, or which is also sparse signal processing. So I will use the term compressive sensing and sparse signal processing almost interchangeably without much difference. So I assume over the course of the workshop, 3-4 days, uh, past 3-4 days, we have probably learned a lot already about the about this paradigm of signal processing. Sparse signal representations, how they work, what are the various algorithms in that scenario, and various results and applications related to that. Okay, so even then, like I will give some brief, I will be discussing some compressive sensing algorithms as well along with the application. Okay. uh, so the problem is DOA estimation. Okay, so my slides are yeah, let me zoom in a bit. So okay, so how does sparsity arise in the direction estimation problem? So we look at two aspects of this. So one is sparse algorithms. So what we do in this is use a mathematical model for direction of arrival, for the observations for various direction of arrivals, and turn them or reframe them in a sparse framework, under the assumption that at any given point a few sources or few directions are active and the rest are not present, which is a very practical scenario. Yeah, which is what happens in practice in any real life example if you take. uh, so it's a basically a mathematical reformulation of the nonlinear problem into a linear problem, and then applying various available algorithms to solve that linear problem, which happens to be sparse. And so you can use the whole machinery of sparse processing and algorithms and representations to address that. Um Specifically, we'll focus on Bayesian inspired algorithms, that is sparse Bayesian learning, which is one of the methods I have been mostly working on. So the second aspect shown here on the right is the idea of sparse arrays. So this is not strictly compressive sensing, I would say. I mean, it is compressive sensing in the notion that you are using fewer sensors in your array. So your array is sparser than using a uniform array, let's say, which is densely samples. But the idea to go for sparse array is not directly inspired by the compressive sensing framework, which relies on random linear projections and so on. Here the motivation is different. Here the motivation is the geometrical structure of the problem, or geometrical structure of the covariance matrix, which is what basically helps us identify the directions. So by exploiting the structure there, and we can reduce the number of sensing points, that is number of sensors, with some assumptions on stationarity of the source signals. It gives us sparse arrays. You're basically sensing fewer points than before, and still able to solve the direction of arrival problem. Okay, so in that sense, it is sparse. It's not the compressive sensing sparseness which comes into it. Although there exists, other interesting literature where people have used actually compressive sensing methods to design arrays, either sparse arrays or some other arrays which are optimal uh, in some criteria. Okay, so that's how broadly speaking sparsity comes into it. So the first part of the talk today, I'll focus on sparse algorithms for DOA estimation, and the second part I'll focus on sparse arrays for DOA estimation. So just outline here. So part one is compressive sensing and direction of arrival. So I've listed a bunch of topics. These are not really the order in which I will cover them. I will cover them in mix interchangeably. Like I will cover them in different order, or I will mix and match. So compressive sensing and the problem of parameter estimation, sparse Bayesian learning, the algorithm, some variation of sparse Bayesian learning with multiple dictionaries, which is useful when you're processing wideband signals, and the application itself, direction of arrival. So we'll look at various simulations and data analysis. So, and the second part will focus on sparse arrays and difference arrays. Why are they relevant? What is the use? Uh, Look at some examples of 1D and 2D sparse arrays such as coprime and nested arrays. These have become very popular in past decade or so. Some algorithms, SBL as C and co-array music as well. And then again, like application, all of these we look at in the context of DO, right? So all these various topics will always be thinking of them or formulating them around our application, which is direction of arrival. Okay, so direction of arrival estimation, I just brief figure. So uh, there is a sensor array 1 to 3 up to m. It could be uniform, non-uniform, it could be linear, it could be planar, it could be non-planar, any kind of all possible geometries are allowed. Different methods may have restrictions on what geometries they can or cannot treat, but in general, you could have any geometry of the array. And the idea is to use observations recorded by that sensor array to find directions of arrivals, of sources. So sources could be acoustic sources, they could be radio sources, or something, some other waveforms. There could be seismic sources, physical pressure waves. So all of these can um, they have same mathematical structure. The only thing is, the physical nature of the waveform changes, but they have the same mathematical structure. So all these signals can be studied under this framework of direction of arrival estimation. So I focus mostly on acoustic signals, but people use these algorithms and methods equally successfully in, while doing, for example, channel estimation, radio communication, right? So that's also there. So to list a bunch of applications, some of you may be working on this or come across this. Um, so smart devices, smart homes, these are very recent ones. So all of these devices have, embedded microphones in them, right? Receivers, either, one microphone or a bunch of microphones, right? If you look at, Amazon Alexa or Google Home, they will have an array of microphones. Right? So a lot of microphones are there. So you can use those to process whatever signals, incoming signals, and find directions. And based on directions, you can give a better service, right? Because you know where exactly the sound is coming from, and then that helps you better identify what is being said, or allows you to focus on specific areas, right? Navigation, right? So autonomous navigation, autonomous robots, this is like a very current topic, a lot of research being done in it. So while you're navigating, you get signals from all directions, various kind of signals, light, audio, radar, lidar, all kind of things. So having directional information accurately helps you do a better navigation, right? Hearing aids, right? These are again acoustic devices, so it helps people listen better who have hearing difficulties. So again, if you can, find directions and try to latch on to those directions, it will be of a lot of use. Surveying help and rescue, so you can have drones surveying some region, and if they are fit with microphone arrays, they can listen to certain, help cries or any kind of activity they want to monitor. Sound source localization in water, ships and marine life. There's a lot of audio sounds or acoustic sounds created by ships, and marine life is also very actually acoustically active. So you can use proper tracking of these things to have a, to do some kind of uh, biological, record keeping or uh, information you can gather from these things. Channel estimation, which is a common radio frequency problem. Okay. Sparse signal processing. So this image is very, you probably have seen this image 4 or 5 times already in this workshop. It basically says that you have a sparse vector m cross 1 sparse signal, right? So colored points are where it's non-zero, everything else is zero, and the number of colored points is very small compared to the length m. And the idea is that you don't want to measure all m points in the signal, but you want to measure only a few points and get a very good or in fact exact uh, m length signal, right? How can you do that, or can you do that, right? So that has been the, the core problem of compressive sensing, and it has many solutions with various criteria, various conditions where it works, where it does not. The main idea is that you need a dictionary, n cross m dictionary, or uh, a random, in some sense it should be random, right? If you have random linear projections of your unknown m length vector, which is the n length vector, then you can recover these signals. And there are some theoretical guarantees for this. So we'll not go into all the theory and these things, but this is just to give the brief idea. Okay. So what are the benefits of CS? So CS is compressive sensing, which is, which I will also call sparse signal processing. Okay. So one of the crucial benefits is, you don't have to sample at the Nyquist rate. So Nyquist rate is very demanding, but for many class of signals, it's not needed. You can sample at many, at much lower rate. So that's what CS tells you how to do that. Okay, and many signals are sparse in some domain or the other, right? So it's helped by the fact that a lot of signals are actually sparse. So we can use this theory. And inverse methods, that is, parameter estimation kind of problems, those are again, inherently sparse. And then, there's this idea of Occam's razor. You might have heard of it. It's basically, if you want to explain a phenomena, I mean, this is a century-old idea, but that's what is the mathematical version of it is compressive sensing, you can say. So if you have a if you have to explain some observation, if you want to explain some phenomena, uh, the one with the least number of assumptions is kind of is very likely the correct one, right? Uh, so that's the idea of sparsity. Okay. And so another thing, so sparsity, sometimes if it may feel that where is my figure? Yeah. So how often do we get the sparse vector, right? Is it so widespread? Uh, so any answers? Anyone wants to say? Is do we very often get sparse vectors, or even if the signal itself is not immediately it doesn't look sparse, but then can you still use these methods?
Transforms.
You can use transforms. Yes. What else?
You can try different bases.
Yeah, different basis is kind of a transform. So any basis change of basis is basically a transform. Yeah, so transforms is one of the main things. Yes. So even if the signal is not sparse in the domain which you're observing directly, but if it is sparse in a different domain, which you can obtain by transforming the signal, even those problems you can solve, right? Uh, Even beyond that, actually, you can solve many problems, even if, it's not a transform, but some other property of the signal. So for example, let's say this signal is, piecewise smooth, let's say, piecewise constant. So again, it has some structure. So the idea is that wherever a signal has a structure, which can be, explained by few parameters or few terms, right? So all those cases are basically sparse for us. So sparse need not always mean there exists a sparse vector. It could come in various forms. So if not, direct transform is one way, but there could be other transforms, total variation transforms, which you can do. And you can find a domain where the signal representation is sparse. Okay, so all those things come under this. So that way it is very generic. It's not a very specialized field, so to say. Or it's applicable to very broad class of signals, because when we say signals, what is signal? Signal is something which carries information for us, right? And any signal with information, more or less will have some structure, which is, that's why we're after it. And as long, as you, when you say signal has some structure, it means you can explain it using a few things, right? Either, orally, if you explain, probably you can explain the signal as a few set of sinusoids, or you can say the signal is piecewise constant, so it only changes it's a few number of points, or you can say the derivative is piecewise constant, and so on, right? So there are various ways to, orally or mathematically describe a sparse signal. So all of these, you can, you can find out some or the other mathematical representation where it is sparse, and then you can just go ahead and apply this method. So in that sense, these methods are very generic. So don't, confuse, or don't restrict yourself to assuming that it works only for sparse vectors. At the heart of it, it does, but if you think of it, almost all signals of interest to us, you can describe them in a sparse manner by using one trick or the other. So that way, it's very, very generic. Okay, that's the broad nature of appeal of sparse signal processing, and that's why almost all research areas have tried to use this formulation in their work. Okay, so that's what I mean. Many signals are sparse in some domain or some way or the other. Okay. So this is the figure again with some equations, right? So the signal model. So my n cross 1 measurement vector y, my matrix A, which I call dictionary sometimes, or it's called the sensing matrix. X is the sparse unknown vector, and there's a additive noise n here. So all of these are the basic framework of the processing. So the problem, what is the problem here? You're given y. You will know the matrix A in most cases. There are cases where you don't know, so that's a different problem. And noise is of course typically unknown, but you may know some statistics about the noise. The problem is to find the vector x with the condition that x is sparse. So that is given to you. Okay. So the problem is to solve for sparse weights or the sparse vector x. There are various algorithms. I have just listed a few. You may have already gone through this, so I will not discuss them in any detail. So basis pursuit or lasso, right? So this tries to formulate the problem as a convex optimization problem and solve it. And there are tons of literature which show that this gives you a very good answer or the exact answer under certain conditions, which are typically about the randomness of the matrix A. And also there will be constraint on how sparse X can be. Okay. There are other methods like greedy methods such as matching pursuit or orthogonal matching pursuit. So they are very fast methods, but they are greedy, so they may not always give you the optimal answer. And there are Bayesian methods, which is fast Bayesian learning. So this formulates the problem in a non-convex format, non-convex optimization problem, and tries to solve it. So it's a different way. There are even other methods such as iterative thresholding methods and so on, soft thresholding, hard thresholding, all those things. So I have not mentioned all those, but there's a bunch of large number of tools available to solve this problem. It depends on what are your conditions, how much do you want the solution to be fast or you want the solution to be accurate, what kind of constraints you're able to satisfy when all those things are there. So the problem is a underdetermined linear problem. Underdetermined in meaning n is less than m. So you have fewer equations and large number of unknowns. Without any constraints, this has infinite solutions. But your constraint is that you want the sparsest answer out of all those. Okay. So the compressive sensing, this is the lasso formulation, right? So I've written here. I think I don't know if I need to write. So the problem, yeah, so I'll write here if I need to. Okay. So the signal model is there. So the problem, to find the sparse solution is basically without any noise. So you need to minimize the L0 norm. So I assume by now all of you know what is L0 norm. It's basically the number of non-zero entries in the vector X. So you want to minimize the number of non-zero entries in the vector X. That is find the sparsest answer subject to y equal to X when there is no noise. And with when you have noise added, you have some conditions because you cannot exactly fit your data in the model. You have some condition on what is the error which is tolerable to you. Okay. So that's the formulation. But this problem is so where is my pen? Yeah. So this problem and this problem, they are intractable. They are what do you say? They are computationally intractable. It's it's a combinatorial problem. Basically, you have to search through all possibilities and do it. It will take you days and years to solve any moderate dimensional problem. So you don't do that. So what you do is convex relaxation. So that is the main breakthrough which compressive sensing literature has allowed you. It says that you replace the zero norm with one norm, as simple as that. So it makes the problem convex. The earlier problem is not convex, but now you have a convex problem. So convex problem means you have a unique, nice answer. You have many different algorithms and tools to solve it. You can use all of these ready-made tools to solve it. And these two problems are the same, right? So these two problems are the same under under some conditions on the A matrix. So RIP conditions and the null space property and all of this you may have heard. So we'll not go into that, but just to mention that it's not always gives you the same answer, but if you design your matrix A properly, it will give you the nice answer. Okay. And of course, you can always rewrite this using a Lagrangian formulation in a different way like this. It just it's much more easier to implement this thing. So L0 LP, these things Okay. So graphical. There's a question. Okay. I thought there was a question. I will continue. So the graphical solution is so again this it's just basically visualization visualization of various LP norms and the solution. So LP norm, okay, LP norm is this thing, right? So NP equal to 0, this is just the sum of not sum. So this is the number of non-zero entries. L1 norm is the sum of mod of each entry, and L2 norm, is the sum of squared of each entry and all this. Right? So very straightforward. So this is the formulation, right? So minimize, very simple case, two unknowns, one equation. Very, very simple. So you can visualize it. Anything more than this becomes tricky. 3D you can still visualize, but more than that you cannot. So two unknowns x1, x2, and you have only one condition, right? So of course it has infinite number of solutions, right? But you want to find the sparsest solution. So you minimize the LP norm, right? So when P is between 0 and 1, so this gives you P norm contours, so which are not convex, okay, or which have this cusp shapes. So you will find sparse solutions here, but there as you go in higher dimensions, there will be multiple solutions. So that's difficulty. When P is 1, you get this diamond kind of shape for the L1 norm, and you're basically looking at intersection points between your straight line and these things, and it is very highly likely that these points will be on the coordinate axis, either the x1 axis or the x2 axis. So that immediately means one of the other terms will be 0, right? So it means, so this solution is sparse that way, right? Because there are only two entries, sparsity would mean basically one is 0 and one is non-zero, right? Whereas if you go for p greater than 1, p equal to 2 would be a circle. So, but in general, p greater than 1, your points of intersection will not be on the coordinate axis. They will very likely be somewhere in between, and your answer will not be sparse. So this is the graphical way of visualizing why L1 norm gives sparse and less than L1 or p less than 1 also kind of gives you sparse, but p greater than 1 does not give you sparse. Okay.
Excuse me there.
Yeah.
P equal to 1, we are getting a line, as you have rightly mentioned. If we take the slope or if we draw that one of the axes is going to be 0, so naturally sparse. Sir, how to justify that we are able to get this shape? For example, if we are going for greater than 1, we are getting a circle and other shape. How to justify it? Because we have the equation a1x1 plus a2x2 equal to b. If we take norm equal to 1, we are getting this shape, but how to justify, sir, that this is the shape for p equal to 1?
Oh, this one you can simply plot in some software also, right? So you can. So what is this? So these curves are, what are these curves? These curves are
Lines.
So this thing is basically mod x1 plus mod x2 equal to some constant. So this, right? So this is mod x1 plus mod x2 is the L1 norm of your unknown vector x1, x2, right? x1, x2 is the unknown vector. It is two-dimensional. So a constant one norm means it's mod x1 plus mod x2 is some constant. And for different C values, you get different diamond shapes. So those are these plots. So
Thank you, sir. Thank you.
So this will always be, for one norm, you will always get these diamonds. And for other norms, you will get more complicated shapes. Okay.
Thank you.
Okay, so this was a general formulation. So now I'll just mention, sparse Bayesian learning, which is our focus algorithm of focus, so to say. It uses a Bayesian approach to the sparse vector finding problem. So Bayesian meaning, it imposes prior and likelihood distributions over the unknowns and tries to find the posterior. Right, so it's randomness included. So it's the randomness you are including basically by some kind of hierarchical modeling. So what you do is, instead of finding the vector x directly, you parameterize it, or you have a probability distribution over x, and you find those parameters. In fact, you can do this hierarchically. So you can have parameters over x. Those can have again parameters over those parameters. So you call hyperparameters and so on. You can have a huge hierarchy. So this formulation, as it has been shown in literature, gives you or leads you to an answer or a case where x becomes sparse. So again, this is the mathematics of that. We won't have time to go over it, but there are literature papers by Rao and group, who have proved these things. Okay. Even the original paper by Tipping. So I have given references in the end. So Michael Tipping, from Microsoft, is the person who proposed this idea of sparse Bayesian learning, or as it was called early by him, relevance vector machines. So, and they show with examples there how this hierarchical Bayesian modeling gives you sparsity in the answer. Okay. So the framework is, just if you were to state it in a few lines, this is how it is. So it is a Bayesian framework to solve problems. So you have priors and posteriors, and you solve for the hyperparameter. Right? So you don't solve for the vector x directly, but x is described by a parameter gamma, and that's gamma is what you find. It needs fewer parameters to solve, or it compared to lasso based method. So because if even if you have multiple x variables to find, you can actually nicely tie them up using a common hyperparameter in the prior, because of this randomness probability distributions. So that way you have fewer parameters to solve for. So that makes your answers a bit more credible, because the same data is used to find fewer parameters. So that way it's more SNR, some way you can think of it. And because of the probabilistic frameworks, it can easily incorporate, any additional prior information. If you have, it's available, you can easily incorporate that in your model. So that's another thing. So we'll see this, we use this in multi-dictionary or multi-frequency formulation of SP. And of course, you can easily process multiple snapshots, multiple frequencies, and all these things. So this is the advantage of a Bayesian and probabilistic framework. Okay. So briefly, I have the model. So I have my equation y equal to x plus n. So I add a prior. I say x is Gaussian. Okay. So here, I mean, in general, it can be complex Gaussian. So because in DOA estimation, y is a complex vector. Your narrowband observations are complex phases and these things. So in general, these are complex. But if it's confusing, you can simply think of them as Gaussian. Instead of complex Gaussian, you can just simply think of them as normal Gaussian, and the theory and all is the same. Okay, so your x is Gaussian with zero mean, okay, and some covariance matrix gamma. And the assumption here we make is, the entries of x are uncorrelated. So it's basically it's a diagonal covariance matrix. Okay, that's the modeling framework of SPL. The likelihood, so you assume the noise is Gaussian distributed again, or complex Gaussian with some variance. Okay, so I have my prior and likelihood. So the data covariance is the covariance of y you can just compute by here. It's the sum of covariance of the noise, that is sigma square I, and the covariance of a into x, that is a gamma a Hermitian. Okay, the simple probabilities. So now what you do is, or what SBL solution is, to solve for gamma. So gamma is the unknown. Uh, Gamma is the unknown we are trying to solve for. Okay. Instead of x, I will solve for a parameter which describes x, which is gamma. Okay, this is a parametric model, right? And the idea is that gamma, if x is sparse, gamma is also actually sparse. Or if gamma is sparse, x is sparse. It works both ways. So that kind of gives you sparse answers. So We do this by what is called evidence maximization. So evidence is nothing but, what is the probability of observing the data, or what is the probability of y. So that by using, probability analysis, it's integration, of p of y given x into p of x, because likelihood and prior, that is, and both of these are Gaussian. So this is very simple. This again turns out to be Gaussian. Okay, and you want to maximize the evidence. Okay, so that's what I do here, right? So the argument gamma, which maximizes p, the evidence is my answer, is what I'm saying. So the small gamma is nothing but the diagonal of this thing, right? So because the capital gamma here, the covariance matrix of x, capital gamma, is a matrix, but only diagonal entries are non-zero, right? I'm only interested in the diagonal. So all those entries in the diagonal, I'm just collecting them and calling them small gamma. Okay, and so my evidence, so this is again, this is my evidence, right? I've just explicitly indicated gamma and sigma square as the parameters on which this evidence depends. Otherwise, it's the same expression as in the previous slide. Okay, so the idea is to maximize this evidence. Okay, or find gamma which maximizes evidence. So this is Gaussian, so you can expand that out, and so basically you will get a optimization problem, right? So this is the optimization problem. It will be, it is non-convex. So that's one of the drawbacks. So you don't have a neat answer, but you can actually use fixed point update rules, and in fact also you can use EM method and all those things to solve for gamma from this. And what has been shown again in literature is that the answer which you get by this method is pretty close to what you want, right? So that's the idea. Even though it's not convex, so there are potentially many answers. So there are many local minima which you will have. But in practice, it works pretty well, and you get an answer which is very close or equal to the true sparse answer. Okay. So this was a single snapshot or single observation formulation. You can easily extend it to multiple snapshots. So this is the multiple snapshot update, right? So this is the equation. So I'll not go into the derivation and equations. So I think you had some talk which was on SBL also. So it's okay. So what I want to highlight here is that how gamma gives you sparsity. So it's a bit tricky. It's not very obvious. So you're finding gamma, right? So what is easy to understand is if gamma is 0, so what is gamma represent? It represents the variance of x, and its mean is anyway 0. So if a specific, let's say gamma 1 is 0, if mean is 0 and variance is 0, it basically means the corresponding entry x is 0. Right? If it's Gaussian with 0 mean and 0 variance, it's basically a delta function at x equal to 0, right? So it's deterministically 0 almost, right? That's how you interpret it. So now that's what I'm saying here. So at convergence, when you do this update rules, your gamma will be 0 for most of the entries, and that's because of the hierarchical framework and all that. So that basically means your x has 0 mean, 0 variance. It means that corresponding x will also be 0. So a sparse gamma implies a sparse x. So a sparse gamma vector implies sparse x vector. Okay, so that is directly related by the formula itself. And why gamma turns out to be sparse? So that for that you have to read a bit more in depth, where you can show, because of the way you have constructed this, gamma tends to be sparse. Okay. And another nice thing is, so if you were to use L1 based methods, you have to choose the regularization parameter so that you get the correct number of non-zero entries. As the parameter changes, the sparsity changes. Right? Not continuously in jumps, but it's still is a function of the regularization parameter. Whereas here you don't have any such parameter. You are basically directly finding gamma. So I mean, you don't have a regularization parameter. So the sparsity is directly present in gamma. So you don't have to tune it or anything. It automatically, in some sense, finds the sparsity. Okay. And the noise estimate sigma square you can find using various methods. Typically, maximum likelihood methods are used. Okay. So here, so why it is, SBL, as I said, it can be much faster than lasso method, especially when you have many snapshots or you have many observations. So why is that? So that's because as the number of snapshots increase, the X increases. So where is my multi-snapshot model here, right? So my capital X, the unknowns, the more Y vectors I have, the more X vector I have to estimate, right? So that's the idea. And if you're using lasso, every new X vector will add to the computation because you have to find that. So your problem computationally scales a lot. Whereas in SPL, what you do is all the X vectors you model it by the same random distribution, by the same gamma parameter. So now you're finding gamma instead of X. So right. So even if you have more observations, as long as those unknown vectors X, they are from the same underlying distribution, you still only have to find one gamma, one covariance matrix, or the diagonal of that covariance matrix. The number of entries do not change at all. The amount of data increases, but the quantities, unknown parameters to find, they do not change at all. They do not increase. So that way, you have fewer, parameters to estimate, and it's much more efficient. It works computationally much better that way. Okay, so the gamma does not depend on the snapshot or the data index. So it's a very nice thing. So here pseudocode is given. I mean, I'll go through it, but just to say that how simple the implementation can be, the algorithm can be. So some parameters initialization, is basically gamma update using the formula given above, and then some breaking, exit condition for the for loop, and this you just run it in for loop. So implementation wise is pretty simple. You don't need CVX and all those tools. You can directly implement using basic MATLAB commands. Okay. Any questions so far? Okay. Let me know if there are any questions. So this was the algorithm part I wanted to discuss. I won't discuss much algorithms after this. I'll focus on DOA estimation. So this application which is of importance to us for today's talk. So this is it's a bit busy slide. So here we are doing writing the DOA estimation problem. It's not as a sparse but as a general problem, right? So what is my observation on the M sensor, YM, right? It is basically sum of signals coming from all the directions or whatever sources are present, right? If there are two sources, it will be sum from source x1 and x2, right? So these are the sources, right? So this is source, this is source, this is my array, right? So this could be any, it could be physics. Sorry, it could be acoustic, it could be seismic, radio. I'm not bothered about that. It could be any array, right? So what I'm saying here is the observation ym is basically a superposition of all the signals coming from all directions, right? I'm sensors and directions, right? So that's my y equal to ax. So y is the collection of all sensor observations. A is now basically this steering vector matrix, and x is the unknown source amplitude, right? So x is the amplitudes of the signals. So this is not sparse so far, right? This is general DOA estimation problem, right? So what is the main principle here is that so when I'm assuming y is in frequency domain, right? So whatever you observe on the array, the phase you will observe will depend on where the source is located, right? For simplicity, assume there's only one source, okay? Then depending on the direction from which the source signal comes, the so the signal will reach each sensor at slightly different times, right? So there is a time delay in the signal recorded by the sensor coming from the same source. By different sensors will record the same signal or slightly different signal because of the noise and all, with some time delay, right? So that time delay, so that's the time domain description. And when you go into frequency domain, the Fourier domain, time, a shift in time basically means a phase change in frequency, right? So that's the main idea, right? So if you look at the frequency domain signal across the complete sensor array, based on the location of the sensor, there will be phase change between uh, the signal absorbed by sensor 1 and sensor 2 and 2 and 3 and so on, right? All that. This from signal processing, Fourier transform properties, right? And when you have multiple signals, is basically a superposition of all those things. That's all right. This is the sum. This is the superposition happening here. All source signals are just getting added up with each with their own complex phase patterns. And the phase, yeah. So this phase depends on e raised to j, this whole thing. It depends on the angle of arrival theta n, the frequency lambda of that corresponding signal, and Rm is the physical location of the sensor, or relative to a specific sensor, where is the sensor located. So the array geometry, the sensor geometry, the angle of arrival, and the frequency, they all of this together decide what phase you will observe on the sensor location. Okay, so this is your problem formulation. So now so this is the problem: y equal to ax, y is given, a is given, x. A is, so I mean, in the general case, the rational formulation, a is also unknown, because a is the steering vectors, the thetas are unknown, right? So theta unknown, x unknown. So both of these are unknown, right? And theta appears as exponential of sine theta. So it's a very highly non-linear problem, right? So this problem is non-linear in theta. It's a difficult problem as such. Non-linear in the theta variable. Okay. So what you do, of course, there are many methods to solve for this. Beamforming, music algorithm, Esprit algorithm, maximum likelihood, all kind of things are there, right? But all of this, they try to solve the nonlinear problem. Where what compressive sensing or sparse representation framework does is, it basically discretizes the set of unknown angles. Okay, No, so I can scan in, let's say, -90 to 90 degree region. Okay, that's my scanning region. At least for a linear array, that's your range. I will divide all the angles into a fine grid, and I'll assume my sources are always on the grid. Okay, that's a small assumption you have to make. So then, because your grid points, you have decided the grid, you know where is the grid. The thetas basically become known, and the only unknown is x. And in the unknown x, the problem is linear. So you can solve it now. Only thing is you have made it sparse or highly undetermined. So DOA estimation is sparse problem, right? So you have n sensors with some spacing, right? So you discretize the angle space, right? So that's the main idea. So the problem is a parameter estimation problem. So this is a angle estimation problem. As such, there is no sparsity. There need not be any sparsity in it. But you are making this into a sparse problem by introducing a artificial grid over the angle space. Example, 1 degree separation angle space you can add. And so now the dictionary A, because you evaluate this at each of the grid points, which are fixed, your dictionary sensing matrix A becomes known, right? So this is known, this is observation, this is the unknown you have to find. And as you see if you have let's say 1 degree separation, so this will have 181 points, -90 to 90, or if you ignore -90, it will have 180 points. Right? So out of 180, it's very likely you will have only 3 or 4 or up to 10, whatever be the scenario, 10 sources, right? Only a few directions will be active for you, not all of them, right? So your unknown vector is now sparse. You only need few directions to represent the whole signal, right? Uh, See, if you think of the Occam's razor principle, right? So you want to explain these observations Y, and you have this whole matrix A to explain it, and this is the X vector. So the idea is, how can you best explain Y? Even though you have 180 columns in A matrix, all of those are not present, all of those are not active. So you want to find only which are present. So only the columns, if you select only the columns corresponding to the directions where sources are present with some proper weighting, weighting would be the source amplitude. Then if you add them, that will basically be your observation, except for the noise part, right? With some error allowed, that is okay. So you're able to explain your phenomena. You see the idea again, it comes, right? So you can explain your observations using few things. Only few directions are possible. Only few directions are active. So that's the main idea. So that's how you make the problem as a sparse problem. That's how sparsity is kind of introduced in it, in the original problem, which is actually non-linear. So the problem becomes linear because of the grid you have introduced. And this then you can solve, right? So this is now a underdetermined problem, y equal to x plus noise. Okay, here the noise term is missing, but noise will be there. And then you can use any method. We'll use SBL, which assumes sparsity, probability distributions over x and the noise and all those things. Only few sources are active. So as I mentioned, only we focus on acoustic sources for examples, but it's any wave-like signals. For any wave-like signal, this will work. Okay. This because the idea is what this superposition, right? So this is superposition. Superposition is a wave property. Superposition. So it works for acoustics, seismics, radio, probably even light. I have not seen people using it for light, but probably they apply. Maybe I have not come across them. It all waves. Radio, of course, so light also, right? Okay. So what are the traditional methods? So SBL is the compressive sensing method we'll use. So there are other traditional methods which are commonly used. So some of you may have come across this also. So conventional beamforming. So this is basically a basically correlation based method. You just correlate the signal with the observations or correlate the steering vectors and find where the correlation is maximum, and then you say in that direction the sources are present. It's very robust to noise, but its resolution is not so good. A high resolution method is music. This is one of the most popular methods, which still people use it. This is a noise subspace based method. So what it does is decomposes your covariance into signal and noise subspace, and uses the noise subspace to find peaks or where the sources are located. I'll just give a brief introduction to these also, and SBL is what we already discussed. Conventional beamforming is basically this. So for all of this, we compute what we call angular spectrum or angular power spectrum. So this is basically a function. It tells you what is the power in what direction, right? So if the power is high in certain direction, in that direction the source is present. So all the DOA problems will be presenting them as power spectrums. Right? So each algorithm computes its own power spectrum, so to say. Power spectrum may not be the accurate word. Sometimes they call pseudo power spectrum, pseudo spectrum, and all this. So the idea is just, it may not be actual power spectrum, but it represents an estimate of where the power is, in which direction the power is high. So that's what it is. So this is basically correlation between the steering vector and the data. So S is the sample covariance matrix. Because you have multiple snapshots, instead of correlating with every snapshot separately, we just combine them into a sample covariance matrix and then use it for computing this power spectrum. Okay, so I'll not go much into this. These are reference methods I will use for comparing SPL. Then there is music. It's a subspace-based method. So we divide it into the covariance into signal and noise subspace, and then you define this power spectrum for music. This is the inverse of this quantity. So so En is a noise subspace. So En are directions, you can say, or not directions. En is a subspace which corresponds to the noise, or which has signal component eliminated from it. So any signal component will have very low correlation with the noise subspace. So if your A of theta, is the steering vector, has very low correlation in the noise, in a specific direction with the noise, then its inverse will be very high, right? So then you will get a peak, right? So that's how the music works. It's called the music pseudo spectrum, and it has a much better resolution than CBF, the conventional beamforming. Okay. So those of you who are working or who have worked on DOA estimation, these methods must be familiar. Okay, so these are just the formulas I've written down, the main formulas for each of them. So CBF power spectrum, music, and for SBL, this gamma is parameter is what I call power spectrum. So it basically tells you for each direction, what is gamma. So it's a variance of the signal, right? If the variance is high, it means there is a source present there in the direction, and if the variance is 0 or close to 0, it's not there. Okay. So some examples, example spectrum. So this is I think a simulated example. So I have taken 20 sensors, uniform linear array. I have 3 sources, so denoted by these red circles, right? So where are they? Yeah, they're at minus 20 degrees, minus 15 degrees, and at 75 degrees. Okay, three sources, and they have different amplitudes, and two of them are very close. They are just 5 degrees apart, which is a difficult scenario to find resolve, right? So I've shown results for CBF and SPL. So CBF, you can see, it will have peaks in different directions. So this is a CBF spectrum. What we are plotting is the power spectrum in log scale. The horizontal is the angle, right? Minus 90 to 90 degrees for each. For some, you discretize the grid, angle grid, right? 1 degree or something. So that is done for CBF as well. For everything, you have a grid. Okay. And in each angle, you find where is the correlation the maximum. Okay. So when you do that for CBF, what you will see is for the nearby sources, there aren't two distinct peaks. They're kind of merged because each peak is so wide, right? So there's a resolution issue. There's a resolution limit. I mean, if you heard of Rayleigh limit, so CBF has that limit. So CBF suffers from that, so it cannot resolve beyond that. Whereas this 75 degree, it can resolve, but the peak is not very pronounced. Okay. Same thing, same result for SPL. If you see, the peaks are very, very pronounced, distinct. And of course there are other values which are but very low values, so they don't even appear in this dB scale which I've plotted, right? So you can very quickly and easily identify these sources using SBL than compared to when using CBF. So this is a resolution advantage which SBL gives you. With music also, it works better, right? So here I've compared a 2D example. So 2D, if you have 2D arrays, such as rectangular arrays or even circular arrays, you can resolve two directions. Okay, so direction of arrival, if you have a linear array, you can resolve one direction. So any non-linear, non-planar array will help you resolve both the directions, right? So azimuth and elevation. So if you want to use the standard terms, azimuth direction, in the horizontal plane, and elevation is with respect to the vertical, and so on, right? So I hope this terminology is fairly standard. So here I've shown an example with the rectangular array. I'm using 100 sensors, a large number of sensors, and the left column is music power spectrum, and the right column is SBL power spectrum. So, and each row has different number of snapshots. So L is the number of snapshots or how much data points I've used. Okay. So as you see, music. Okay, again there are three sources indicated by red circles, and yellow is actually a high value, so it indicates the source has been identified, and blue is a low value. So because it's 2D, I need to plot them as images. Earlier it was 1D direction estimation, so I could plot them as a X versus Y thing, but here I need to use images to plot power spectrums because you're finding the power spectrum for every azimuth comma elevation pair of angle. Okay, so here if you see for L equal to 10, it's very few snapshots. Music cannot distinguish the two nearby sources. It's a two nearby red sources, whereas SBL seems to work very well already. And then I gradually increase the number of snapshots down the rows, 50, 100, and 500. So maybe near 100 or 500, music is able to resolve them somewhat. So that's the disadvantage, that music needs a large number of snapshots to work well. Whereas that's not the requirement for SBL. Even with few, sometimes as few as one snapshot, you can get good results. So that's the, it's working, it's able to resolve even better than music. That's what I'm trying to show here. Okay, so these are some, yeah, basic examples to compare traditional methods with SPL. So one can also, people have done it. You can also apply other methods, compressive sensing methods, such as basis pursuit and lasso. So they will work somewhat similar to SPL, but our preference is using SPL as it is faster and especially when you have multiple, if you're processing 500 snapshots, SBL will work very fast compared to how much time the lasso algorithm will take. It will be very slow. Okay. Any questions so far? So otherwise, I will move to a discussion on a variation of SBL. SBL using multiple dictionaries. So multiple dictionaries. So the idea is, something like this. So the equation, at the end, if you see, I'll highlight it. So earlier, when we say multiple snapshots, what we assume is the same A matrix is there, but X is slightly different and Y is different, right? So that is, so it's a single dictionary. All observations are tied up by single dictionary. And you can use regular SPL to deal with it. But in some cases, you may have a different problem where the dictionary is different every time. Right? So the dictionary also. So each observation is from a different dictionary. So examples where this will happen is when you have multi-frequency data. Okay, very common example. So this is because if you look at the A matrix, steering vector matrix, go where it is, yeah, right. Steering matrix A consists of steering vectors, these things, and these depend on lambda. You see, so lambda or the frequency. You can write uh, this in terms of frequency as well. So A is frequency dependent matrix. It's depending on what narrowband signal you're processing, your A will change. But many times you have broadband signal. You record signals at multiple frequencies together, or you record a time domain signal which will have multiple frequencies. So your observations at different frequencies will depend on a matrix which is also different for that, or it depends on that frequency. So how do I use now how can I process this data? My earlier tools will not work because they work under the assumption the A matrix is fixed and known. Here also it is known, but it's not fixed. It's changing every time, right? So that is the idea of SBL with multiple dictionaries. So you have YD, each, so D is the index of observations or the index of dictionaries, so to say. So each observation potentially depends on a different dictionary. And I now want to process this. So the idea is X here, X is also different, but the support of X is still the same, right? So there is a common support in X. X is sparse, its entries also may change, but where it is sparse, that does not change. Or to put it differently, I am only interested in the part where the sparse, where I'm only interested in the common part of sparsity of X. That is of interest to me. Okay, and you will see a nice example where aliasing can be avoided by this simple, nice trick. Okay. So I hope the idea of multiple dictionaries is clear. So I'll formulate this within SBL. So what we do is we have various prior models for this. We'll discuss two of those. So this is the observation model, right? Each dictionary gives you different observation. So this is the multiple covariance prior. So what you assume here is X itself depends on gamma, which is dictionary dependent, right? So XD is dependent on gamma D, and the each dictionary it is different. Okay, right? So this is the the earlier model, or it's a simple model, but it has some advantages. And then you can say the final effective gamma will be this is the average of these things. Just you can combine, because eventually you're only interested in a single sparsity structure for the x vectors. For different x vectors, I am interested only in the sparsity structure. See, direction finding problem does not actually need the x itself. You only need to know where the x is non-zero, because that tells you the direction. If you're interested in the source amplitude, then the whole x vector is also useful. But as long as you're only interested in the direction, just knowing where x is non-zero, or just in fact you don't even need x in the SBL framework, only finding this gamma vector which parameterizes x, where the gamma is non-zero, those are the directions. So that itself is sufficient. So that's what we do. For each observation, we assume a different dictionary. Or for each observation which depends on different dictionary, we assume a different gamma, find that separately for each of them, and just average them. This is called incoherent averaging. So this allows for variations across dictionaries, but it does not it's not efficient, it's not not good at finding the common sparsity. That's what we observe. And this is another model, that is common covariance. So here what you do is, irrespective of D, you assume it's the same covariance gamma, right? So previously you introduced gamma D for each D. Now I'm saying no, I don't want that. I just want a single gamma for all dictionaries, right? So this way I have much fewer parameters to estimate. Again, you can derive update rule, apply the formula. The nice thing about this is it kind of, by the way you have modeled itself, the sparsity is common across all the dictionaries. The sparsity in X is common across all the dictionaries. So when that is true, it works very well. The disadvantage would be that it does not allow, it does not, it's not able to capture any variations in sparsity across dictionaries. And that is okay, because it depends on applications. So in some applications, this model may be useful. In some applications, the previous model may be useful. Okay. And I'll show an example of aliasing. So I hope people are familiar with aliasing, right? So at least within the Nyquist sampling situation, right? So if you don't sample at the Nyquist rate, if you sample at a lower frequency, you will see aliasing, right? So that's the time domain sampling and time domain aliasing. Here what we have is a spatial aliasing, right? So that means if your sensors, so there's a requirement that the sensor spacing, at least for a uniform linear array, if you look, spacing between the sensors should not be more than half the wavelength. If it is more, then you will see aliasing again. If it is less than that, you will not see aliasing. At the same time, you also want the aperture, that is the whole the length of, or the area of the array to be as large as possible, because that dictates how focused your beam will be, right? How good resolution you will get. So there's always this trade-off between the aperture, which you want to be as large as possible, and between the spacing between the elements, which should be small, so that you can process more frequencies, right? If you want to process higher frequencies, it will have smaller wavelengths. Smaller wavelengths meaning your spacing should be smaller than half wavelength. So it has to be smaller and smaller. So there is always this opposing things which you have to balance out while designing an array. Okay. So what I've shown here is, a histogram of SBL output for, again, three sources are present, three red circles. So the first panel is, the spacing is half wavelength exactly. Okay. This single frequency analysis. So if you have half wavelength, if you see all your SBL peaks, so the histogram, the bin count is the histogram is where I found the SBL peaks. You see, they are always nicely near the actual true source locations, the red circles, in the first figure. Whereas second figure, I have not followed the Nyquist criteria for spatial sampling. Basically, it's equal to saying I am sampling at a rate lower than the Nyquist rate. I am sampling spatially at a rate lower than the Nyquist rate. So hence I will see aliasing. So apart from the three correct peaks, which I see, I also see three other peaks. They should not be there. This orange crosses, right? They should not be there because they are just false versions of the other peaks. They are not true sources. There is no source there. Right, that's what happens in aliasing. Even high frequencies appear as low frequencies. Same thing here. A specific angle appears as some other angle. So this is aliasing. So when you do single frequency processing and you have not satisfied the Nyquist sampling criteria, you will see aliasing even with SBL. But when you do multi-frequency processing, when you smartly combine them, so what happens is even if there is aliasing, see, you may have multiple frequencies. Some frequency will have aliasing, some may not. Right. So for a fixed array, fixed array spacing, a lower frequency will not have aliasing, whereas a higher frequency will have aliasing. So that's what I have done here. I have taken two frequencies. One of them experiences aliasing, other does not for the given geometry. Okay, aliasing is geometry dependent, array geometry dependent, right? So now, even if some frequencies have aliasing, I am enforcing a common sparsity. So the two SBL methods I discussed above, multi-frequency methods or multi-dictionary. If you look at the bottom figure, common sparsity, common covariance, because I am forcing all of them to have same sparsity, even in spite of presence of aliasing, my algorithm is able to return in the correct histograms. That's because other locations are kind of suppressed because of the condition of common sparsity. Whereas the other, MC method, multiple covariance, where you solve each frequency data separately and then you average. So some frequencies will experience aliasing and some will not. And when you average them out, you will get false peaks in these locations. So this cannot be avoided. Okay. So this is one example which shows you can even in spite of having data which can possibly be aliased, if you smartly design your model and use your algorithm, you can get rid of some problems such as aliasing. The same examples differently or different examples showing the same thing rather. So conventional beamforming. Okay, so this is angle on the horizontal axis. So if you see, for lower frequencies, I'm going from 600 to 1500 here. Okay, so CBF for low frequencies will not show, anyone will not show aliasing, but as I increase frequency, this additional, so you have to look at horizontal cross section of these images. Okay, so horizontal cross section, if you look, there are actually only 4 sources here. But if I were to slice it like this, let's see. Okay. If you see CBF, you'll have 1, 2, 3. So yellow parts are all the sources. 1, 2, 3, 4, 5, 6. So you see 6 peaks here for CBF where I've sliced this, right? So even though there are 4 sources, because of aliasing, 2 more false peaks have come in, right? And you cannot avoid them. And even now when you average, so the bottom panel is basically average of this thing. Even when you average, it does not look very good. It's CBF again has its own resolution issues. But even the multi-frequency method, so this is the CCSBL and this is the MCSBL. The name has slightly changed here in my slide, but I call MF1 and 2, but it's the CC and MC. So if you see the MCSBL, because for each frequency it processes separately and then averages, you will see all these false peaks coming in. Though they are of lower amplitude, this problem will become worse when SNR is low. Whereas in the common covariance formulation, where you force all of them to have same sparsity, there is no false peaks. There's only the true peaks are there. So it's again, basically you're avoiding aliasing here. So this is again aliasing example. So yeah, so you have to choose your SVL, your algorithm and your model as per your requirement. Okay. So some more applications. So this was multi-frequency SBL. So here a couple of more application or examples of DOA estimation. So there's an open source data set called Locata dataset. So localization and tracking. So I don't know if has anyone heard of this data set, or is anyone working on this? Okay. So if you are interested in acoustic source tracking, array-based direction estimation, this is a very interesting data set. So they have recordings from various microphone arrays. There some are linear, non-linear, non-linear, all kinds of different arrays. And they have provided basically different tasks. So you have a single speaker, moving, speaking. So basically, I've given you acoustic recordings, microphone recordings, and they also give you the ground truth of the actual source location, right? So it's a data set which is useful for comparing and benchmarking, right? So there are various tasks. So some of them have moving sources, some of them have single, some have multiple sources. In some, the arrays are moving. All kinds of scenarios they have considered. It's very interesting. So any algorithm you come up with, you can just quickly test it on that data set and see how where your algorithm stands compared to other algorithms in literature. Okay. So the processing is as before, very simple. You have audio recordings. You take short time Fourier transform. So all the methods I discussed are frequency based methods. So you do Fourier transform before processing. There are other time domain based methods as well, which people use, such as GCC FAT, SRP FAT. So I'm not including those in this discussion, but those are also some methods you can use for direction estimation. That's a different discussion again. Okay, so take Fourier transform, right? For each block, so you do block level processing, and for each block you estimate, all the DOAs, right? So localization algorithm is basically, DOA estimation or spectrum finding, right? That, right? So find or estimate spectrum, and then from the spectrum you find the peaks. So that is the DOA extraction. You find where the peaks are present, and those will give you the location of the of your source directions, and then you do some error analysis. Okay, So we implemented wideband music and CBF by just averaging each across frequencies. Whereas for SBL, we use this common covariance method, which kind of inherently does combination of all the signals, all multi-frequency signals. Okay. So some results of this of processing of this data set. So again, so 2D directions you can find because these are complicated arrays. It allows you to solve for the 2 directions azimuth and elevation. So a simple spectrum comparisons. If you see CBF, so the 2 columns represent 2 different microphone arrays, and each row is a different algorithm. So CBF has poor resolution. So the red cross is the true source, and circle is your estimated peak. But you can see the peak is very broad in CBF. It's improved in music. It's much better. You can see it's more localized. Whereas when you go to SPL, it's much more localized. So it's a very sharp answer you get. So this helps us, in basically see that how the different algorithm resolutions compare. Okay. Yeah. So this was for one, a single block. So this result, for example, if you go in this framework, so one of the blocks when you process, you'll get this thing. Now, of course, say it's a continuous stream of data. You want to, localize over time, constantly keep on tracking the source. Right? The angles may be changing. So that's what we have done. So multiple blocks we have processed over time where the source is moving and its angle is changing. So left is the azimuth angle, right is the elevation angle we have shown. Elevation is constant, because it's a person with some microphone, is moving around. So the elevation does not change much. The azimuth changes with respect to the array. Okay. So again, 3 different methods. The same methods are compared. You can see, SPL is much more accurate in finding the direction compared to the other methods. CBF has low resolution, you can see. Music is definitely improved over CBF, but it can have, false detections and these things, which are much reduced when it comes to SBL. Okay. So these are, some data processing which we have done. So Locata data set. So one of the tasks in that I'm displaying here. So you can do overall error analysis of the whole data set. So here, so task wise we have done averaging for various. So each task has multiple audio recordings and different cases. So the mean absolute error, if you look at, CBF stands out a lot. So it has high error, low resolution. Music is better in tasks 1 and 5. In 3, it's a bit worse than CBF. That may happen, when the assumptions are not working properly. Whereas SPL, if you see, it's pretty good. It has one of the lowest errors in all the tasks. So on average, also, it works very well. Probability of detection. So this is, basically, this is capturing the resolution abilities. If I go back, this thing, right? So because, when you have spread out peaks, especially when there are noise, your estimated peak may be much farther from the true peak, right? So that again contributes to the error in your algorithm, right? So if I look at it, detection probability. So what is detection probability? Is basically a fraction of sources I am able to detect. Okay, and how I calculate that? So there's a cutoff, horizontal axis is cutoff angle. So if the estimated angle is more than some zeta degrees away, then I say it's misdetected or it's not found. And if it's within that, I say it is correctly detected. So it adds to the detection probability. So the formula is given. So for various cutoffs, you see. So if I look at, let's say, task 5, okay. So the dotted dashed line is SPL, red is music, and blue is VF. So if I see, let's say 5, cutoff value of 5 degrees. So what it says is, uh, so for 50%, close to 50% of estimated angles are within 5 degrees for CBF and music. Whereas for SBL, it is crossing that almost at 70, between 70 and 80, let's say 75. So up to 75% of detections are within 5 degrees. So it is, more concentrated. Your peaks are better resolved. And so this SBL is always higher than the other two. It means it, at least for task 3 and 5. Right? So it's this is another way to say that your peaks are in the correct locations, right? And you're better able to track and localize your sources. Okay. Any questions at this point? Okay, so last couple of slides for this session. Then we'll have a break. So above was Locata dataset, which is a above ground audio phone audio recordings basically. But the same principles applies even if you go underground or underwater rather. Sorry. So a lot of research happens by acoustic monitoring of you know underwater regions, oceans, and that's because sound waves travel much farther, at least lower frequencies, within the water. So it's a very good tool to study ocean environment. Even things like the speed of sound changes as the ocean changes. If the ocean temperature increases, it affects the speed of sound, and you can do that calculations and inference. Or the salinity of the ocean, or the pressure, or or the turbulence in the ocean. All these things contribute to sound speed and all these things. Right. So underwater, signal processing, underwater acoustic signal processing is a very active research area. So when I was doing a postdoc work at Scripps Institute of Oceanography, there they were interested in all these things. So what you do is, where this cartoon says here, this red beads kind of thing is the microphone array. So what you do is you have a research ship or any ship. You attach this array to this. It's a long array which goes into the water, and you will have some source. There will be another ship which will be an active source, or you could be monitoring natural sounds. That's also fine. So these are called hydrophone arrays. I mean, so these are basically same as microphones, which we use above in air, but these things work in underwater. They have to work in water, so they have different structure and different geometry. So these are called hydrophone arrays. But what they are measuring is basically again sound speed or pressure waves. So you deploy this thing, and so again, same thing, direction of arrival. So if you see the the right image, if you have a source present, even if it's a single source, because of the sound waves will get reflected at the bottom surface, at the interface between air and ocean, the reflections happen. Even if you have one source, you may have uh, the signal coming on the microphone array or on the hydrophone array from multiple directions. So all those directions you would be interested in estimating. Okay. And this shows the geometry, the water sediment layer bottom. So this is all this stratified surfaces which are of interest if you're doing more oceanography kind of research. Okay, so this is result from data which was processed from this. So there is a ship noise data. So what we have is a hydrophone array, and there's another ship which is basically each ships make a lot of noise, a lot of acoustic noise underwater, right? So that noise is basically recorded by some hydrophone array. Okay, there are two ships which were sent for this research purpose, and the ship is basically moving. It's not a stationary ship; it's moving. So as the source moves, the directions of arrival keep on changing, right? Because the reflections will happen at different angles and all these things. From where the source, you record the signal, the direction changes. So that is what is being we have tried to estimate it here. So horizontal axis is time axis. So over time, the ship is moving. So the first panel shows you how the ship is moving. It's not very clear. It basically tells you how far, in kilometers is one ship from the other, or is the noise, is the sound source from the recorded microphone. Okay, so see, it's in kilometers. So over kilometers range as well, you can uh, actually hear the ship sounds and these things, right? The second panel is based on a simulation. So okay, so I've not labeled this, right? So second panel is the directions of arrivals uh, from simulations. You have softwares in which you can feed in, you can feed in the known geometry, the known geography of the region. How deep is the water? What is you know what the properties of the air water interaction or air water surface, and the mud below. What is the reflection coefficient and all this. So which uses all this information and sound speed and temperature and all this to give a estimate of where you should you know how the sound will travel and what directions you should see. That's the second panel. Okay, so for example, at time 10 minutes, if I see, so you have to vertically slice this. Okay, so this colored dots are basically the directions. So my direction is vertical here. My vertical axis is direction here. Okay, direction meaning DOA, right? So DOA. So this is DOA. These are all DOAs. Okay, now vertical axis. So it tells you at what time, what angles your array should be noticing, because the source is present in so and so location. Okay, so the simulation, that's the reference point for us, the simulated answer. The middle panel is CBF results, compressive, not compressive, conventional beamforming. Uh, as you can see, it can find some of them, right? So these bright yellow lines are the actual DOS. The blue part is low amplitude and the yellow part is high amplitude. So those are the peaks. Those correspond to the directions. So you can find some directions, strong directions, but otherwise the image is pretty blurred. Then the last one is music. And the fourth one is SBL algorithm. So throughout this talk we are always comparing these three. So again the same three. Music, you see, again it's much better than CBF. You can see much more nice patterns in there, which kind of match the simulated answer. But there is some blurriness. Whereas if you look at SBL, it is very very sharp. It's very nicely able to track, identify the small, very localized answers, right? especially, you know, if you see around, let's say 25, right? If you vertically slice at 25, the music is showing a very, yeah, I have it in the next part of the slides, I think. A very blurred answer, and CBF is also having blur, whereas SBL, if you see, if I were to zoom in, you can see, you know, it can find all these small separations, all these nearby angles it's able to find because of its high resolution ability, right? So that's the advantage of compressive sensing methods. Uh, so I think, yeah, I will stop here for this session. So some references I've given. So the first paper is the actual original SBL paper, and some analysis by Rao and others. And I've also included some of my references. Some of the work I've done in this DOA estimation, SBL, multi-dictionary SBL context. Any questions? I have not seen the chat. Are there any questions in the chat?
The underwater localization, what are all the noise or what are all the disturbances we need to consider?
Underwater, I mean, there's a lot of uncertainty in underwater, you know, because I mean, there are of course natural sounds. The marine life itself, there's a lot of sounds, and if you are near some port region, in your coastal regions, there will be a lot of activity, a lot of ships and trawlers and fishing ships and, you know, goods transport. You know, a lot of activity, economic activity happens in the ocean these days. So all those things contribute to the noise, but that's okay, because I mean, what many times the aim is to monitor that noise activity, to find out where there is more
Okay.
noise, where there is less, how the man-made noise affects marine life. You know, it's, it's an ecological problem also. You want to figure out where there is more noise, you know, if it's affecting, you know, how the fish population changes, for example, right? So those kind of studies also it's useful.
Or another vessel, if some other vessel interrupts.
Yeah, yeah. So of course, so this is again, you know, ship noise. So this was more like your research. So this is some actual data set which the research institute where I work with collected this data set. So they sent a ship with a hydrophone array attached to it, and there was some traffic. You know, there's a ship traffic also. There are ship routes and roadways, or whatever, waterways. Sorry. So along that waterway, some ship was going, and this is the analysis of that ship. So yeah, so if there are multiple ship, you will see multiple, you know, much more crowded DOS and all that. Does that answer your question?
Yes, yes, thank you.
Okay.
Sir, just one query, sir. Sir, what is eigen mic? Sir, in one of your slide, I found eigen mic and eigen rays.
Oh,
Sir,
it's
in this
just the
slide,
name of
eigen rays,
the array they have
that
used.
term is there. In some of the previous,
No, they are different.
yes.
Eigenrace is different from eigenmix. Sorry. So eigen one. Let me clarify. Eigenrace. Yeah. So this is the name of the algorithm or the simulator which generates this simulation. Second panel.
Okay, okay.
It's the name of the software.
Okay,
And
achha,
that is
okay.
completely different from eigenmic, which is name of the array which I mean, the people who made this data set, given the reference in the bottom, they have called this eigenmic. Or I think this is the commercial name of the microphone. It has 32 microphones on a spherical array. It's probably the commercial
Okay.
name of the microphone or the people who sell this microphone. So that's why it's called eigenmic. They're different. It's not, yeah, the two eigenmic and eigenrace are not at all related.
Okay. Okay.
Sir, I have also I have also one query, sir. In
Yes,
might
yes.
in SPL with multiple dictionary, you have one term called face only multi snapshot data. Sir, what is the
Hmm.
meaning of that? Uh, Sir, one more. Yes, sir. Here, face only multi snapshot data. What is the meaning of that, sir?
Yeah, so I didn't discuss this another application. So phase only. So our observations are, these y vectors, right? And these are, in general, they have amplitude and phase. Uh, but sometimes, especially when the SNR is low, amplitude is less reliable. So what you do is you only use the phase information for your analysis. You extract only the angle part of this complex quantity y. So, and that's what I mean, the phase only information. And multi snapshot means, you have multiple y's. So if you have y1, y2, L snapshots, there's multiple snapshots. For each of them, you just take the phase information. So that will be the phase only data.
Okay, sir.
So
Sir,
when the
another
noise
query,
is
sir.
high, it is used. Yeah, go ahead.
Sir, sir, above here, the noise is modeled as Gaussian noise, sir. Below water, the noise is also modeled as Gaussian noise or some other noise, sir. Because medium is different, no, sir.
Yeah, medium
Above
is
ground, it
different.
is no.
Yeah, so that's the modeling assumption which SBL makes. So it assumes noise to be Gaussian. There are, I think there are other variations of it where you may assume a different noise model and may be able to solve it. Only thing is, without Gaussian noise, it becomes much harder to get the update rule and develop the SBL algorithm. Hence, we use the Gaussian noise assumption. Uh,
Okay,
what Gaussian noise can is usually justified by the central limit theorem, where because
okay,
noise is not from one source, typically many sources are there above air or underwater, and all this when all the sources come together, it's kind of Gaussian. So, but that's an assumption, yeah. So it may not be actually Gaussian. So then your answers will be less reliable, and you may have to go for other complicated noise models.
okay. So, sir, central limit theorem. So, based on that, all will be Gaussian noise. All will become to Gaussian
Uh,
noise. Okay, okay, sir.
Yeah,
Okay,
so central limit theorem is very useful in that context. Then just how actually that's how you justify the Gaussian assumption very in practice, because we typically won't know all the sources of noise, but there will be many sources of noise. So and they add up together, just some of them. So by central limit theorem, sum of many different random variables, if you just add them, it tends to behave as a Gaussian nature. So it does not
so
always
one.
work, of course. For example, in communications, you have this Rayleigh fading and all. That is not Gaussian because it has a different problem, a different geometry. It works differently. So you may need other assumptions. Uh, Here it makes the algorithm development easy, hence the Gaussian assumption is used. It's not actually based on the actual noise modeling and all. It's based on what makes my algorithm implementable. That is the main consideration here.
Okay, thank you.
Yes.
Excuse me, sir.
Yes, sir.
Excuse
Go
me.
ahead.
As, uh, actually, when we use that sparse Bayesian learning, what are the challenges in estimating that if you use, say, whether it will be a complexity problem or
The
what will be
challenge
the
is
challenge?
so compared to CBF and music, it is still much. It takes a lot of computations to solve. So that is one challenge. Other challenge is see, all these methods are grid-based methods. So your true source has to be close or somewhere near the grid, or even if it's not, what you will estimate will always be on a grid. So if your actual source is in 10.5 degrees angle, you can only estimate either 10 or 11. So that error, that is there. So people have developed grid-free methods, which work slightly differently for that, or they do grid correction. They estimate on the grid, but later they do some corrections to get improved results. So that is one challenge. Other is challenge for tracking over time. So if I go to my processing this thing, typically what we do is we take blocks and process within a block. We assume the angle is constant and estimate, and then move on to the next block and so on. But that may not be the case. Within a block also, if the source is moving, there will be some movement. So those you are not able to capture. So that is another challenge. What else? Yeah, so computational things, assumptions. Yeah, assumptions, again, the Gaussian assumptions, the noise assumption, the previous question, right? So if those assumptions are not valid, then your algorithm may not perform as well. So that's another challenge. And also like for multiple, so for 2D direction estimation, your grid becomes much more bigger. So 1D may have 100 points, but if you have 2D, we need 100 into 100. That is, it's 10,000 points. That makes the algorithms very slower. So those are again challenges. Yeah.
Is there any method to just lower the resolution, that is making the resolution higher of that grid, and then using that
So simply
SBL, we
making
can
the
able to.
resolution higher does not work because you have a lot of coherence. Your steering vectors will look very similar to each other. So so the compressive sensing also has a limitation where if your dictionary matrix, right, the A matrix, the sensing matrix, it has highly coherent columns, it will not work well. That is another issue one has to deal with. Simply increasing the grid resolution, even if you have computations, simply increasing them will not help. It will only help up to some point, but after that it becomes difficult.
Whether the structures, if we find some structures and then introduce some, and then if you use SBL, will it help to reduce the to increase the resolution and
So what do you mean by structures?
structures? Finding that from that grid points, say some blocks, uh, block
So what
sparsity,
we
something like.
so what people do is refine the grid. So first take a very coarse grid and then refine it. So first take only 10 degree separation, so it's a small grid. Find where is the source and then focus on that small area and then take a so maybe that kind of structure you mean. So that is one way people do things.
Okay, so two steps we have, we can
Yeah,
go.
two or multiple. Yeah, can you have a hierarchy of grid? Yeah, that you can do.
Yes, sir. Thank you.
Okay.
Okay, sir. Thank you.
Any queries from participant side? Okay. Sir, with your permission, we will stop this session here and let's just take a short break.
Yeah, sure. So we start at 11:30.
Yes, sir.
Okay. Yeah.
Okay. No, I request
Okay.
all the participants to take a short break and come back by 30 minutes.